So last time we talked about inductive types, so inductive type structures and classes, as just sort of the summary of the class, we learned about inductive types, how they can be introduced, they have parameters and indices, we can work with them by pattern matching, using cases in induction, and then you can construct structures with various methods, and using type classes to do a sort of backtracking search to help generate these. There was one extra thing that I wasn't able to get to for time from the previous class, so I'll talk about that. And today we'll be talking about how to search for theorems in Lean and mathlib. And if we still have time, I'll do some live formalization and try to, I don't know, demonstrate something about how formalization works. Our cases are intro and obtain. So I already showed you how if you have an inductive type like this P and Q, you can destruct it by using cases. You get cases for each of the inductive constructors. In this case, it's just one. You get these A and B, which are proofs of P and Q. When there are multiple, they appear like this. So this works on and, this works on or, this works on exists. When you have multiple exists, well, you have exists A, B, and C, sets of P of A and P of B and P of C. Then pattern matching on each of them, well, you have to do something like this, right? And that gets a bit annoying. Our cases is kind of, it stands for recursive cases, and the idea is that it allows you to do a bunch of cases at once. And so you give it a sort of pattern here that's right associated, so these are the same. You get out all the pieces. There's an alternative syntax for this called obtain, where it puts the pattern on the left. And you might notice that this is kind of similar to have, and actually in this case, you can also do the same thing with have, because have also takes a pattern. So you can pattern match multiple things at once. And you can also pattern match multiple things at once using match. These two are using a slightly different syntax though. They look the same in this case, but one thing that you can do with obtain that you can't do with have, because it's not syntactically correct. Here you can pattern, in this case, this was exists with an and, but here we have exists with an or. So exists A, B, and C such as P of A or P of B or P of C. And so this expression here is like a P of A or P of B or P of C. And I want to pattern match it to get the three cases. And so I can basically just write all the patterns up front as opposed to match, where you have to write the various different cases like that. So when you use obtain, you just call the tactic, and now you get a subgoal for each of the cases. And they've already been named. So like in this one, each of A is named, and here you have each of B, and so on. If you wanted to do the equivalent with match, it's a bit more verbose. You have to say A, B, and C, and then all of the cases. Our intro is a version of our cases where you are doing introduction and then immediately casing on the result. So here we're doing sort of the same thing, but notice that the difference is here H was already introduced. So in this previous state we already had H and we pattern match on it. In this state we just have a function type, and so this is sort of equivalent to saying intro H and then obtain. Like that. Okay. And so recall our previous. Oh, questions?
If it's left associative anywhere, like if you had a parenthesis around the left and or left or in the case, how would you do it?
Well, maybe I'll demonstrate it on the and. So here in match, you would angle bracket like this.
Oh.
And it's the same thing in obtain. It's left associated. So if you want to, it's right associated normally. So if you want a left associated version, then you just write it like that.
Do you need to name all of the variables because not all of them happen to appear on the right hand side?
Yes. So in this case, actually, I mean, all these proofs are trivial. So we actually don't need any of the names. So I can also just name them so there's actually a couple different things that you can do here. So one of the things you can do is you write underscore, and it leaves it in the scope with an unnamed thing. The other thing that you can do is dash, and that actually deletes the assumption from the context. The difference between these is that when it's gone from the context, even things like assumption won't find it. Whereas assumption would be able, like I can still, like here, I can prove PA by assumption. So I can still sort of recover the fact that it's in my context. Whereas if I do this, then it doesn't work anymore. So that is useful also if you just want to like remove, like if it's really big and you don't care about it and you want it to go away, then that's useful. It just is clear. Okay. Any other questions? Okay, so I wanted to show you, so this was our proof of that we had this definition is even, which was an inductive predicate, and then we proved that it was equivalent to being equal to the double of a number. In this proof, we did intro, and then we got an equality, and then we rewrote with this equality so that instead of saying is even n, it said is even 2 times k. And then we got rid of the equality because it was going to get in our way. If you recall, it gets in our way because it messes up the inductive hypothesis. So we want our inductive hypothesis just to say is even, so we clear it. So let me show you how we can do that in a slightly better way using, I think this is actually the same. I can show you how we can do this in a better way using our intro. So there's another pattern that you can use in our cases patterns, as they're called, which is REFL. So instead of writing EQ here, I write REFL, or REFL, I guess. And what this does is it sort of pattern matches on the equality and immediately replaces all occurrences of one side, which is a variable. So here our equality was n equals 2 times k. So when we use REFL, then it just replaces all occurrences of n with 2 times k and deletes it, which is basically exactly what the 3 lines from before did. So this is just another way of doing it, which is shorter. Oh yeah, and this is the equivalent using cases. Yeah, so our intro is doing the equivalent of intro. So like it first introduces the variable, then it does cases on it, it gets these two things, and then it uses the substactic, which I haven't mentioned before, but the substactic takes an argument which is an equality, and then it eliminates occurrences of one variable on one side of this equality. So in this case, it deletes n, it deletes EQ, and then it replaces all occurrences of n with 2 times k, like so. Okay. Any questions?
REFL is from reflexivity property?
Yeah, so REFL is reflexivity, and the idea is that this is very similar to pattern matching on an equality, and the only case is reflexivity.
Wait, so this is the constructor REFL, not the tactic REFL, but they would both work in this instance?
This is actually the R cases pattern REFL. This is specific syntax to this thing. Like if I wrote EQ.REFL, it wouldn't work. It doesn't actually accept identifiers in general. I mean, except for naming things. But REFL specifically is accepted in this position, and it calls subst specifically. So this is just one extra sort of. Maybe there's some comments on. Where there's R cases. Did I have an example of R cases? I feel like I must have. Yeah, so the docs on R cases tells you all of the possible R cases patterns. Can I make it a bit bigger? And so you can have a name, you can have a blank, we saw that, a hyphen, which clears the active hypothesis, a keyword REFL, which does this substitution. You can also do type descriptions. We saw tuples and we saw alternations. And you can also put @ signs before tuple patterns. But yeah, that's basically everything you can do. Okay. All right, so on to the main topic. So I want to tell you today about how you can find things in mathlib. So mathlib is a very large library. It's larger than Lean itself, and it has many, many theorems. So one of the issues that you're going to routinely run into when you're trying to formalize anything really is, where are the theorems that I want? Like, I have a feeling that someone has already proved it. You know, I want to rewrite with associativity of natural numbers, and like, yeah, sure, maybe if I had a bunch of time I could prove that myself, but I don't want to because I know that it's already been done somewhere. And I just want to refer to that. So, but I don't know the name of the thing. So how do I find the name of it? Well, there's several. I've ordered these roughly in increasing level of sophistication. So our level 1 here is grep the sources. So this is surprisingly effective, and you know, don't knock it until you try it. The idea here is we'll get mathlib. So I'm going to open up mathlib, the repository, and then I have all of the files available here, right? And so I can sort of, you know, click through and whatever. But I can search for a, let's say I want to know about, I don't know. Someone suggests something that I should search for.
Euclidean geometry.
Can you make the font a bit bigger? This is. Thanks.
So, see, one of the advantages of searching in the sources like this is that we don't just get hits in Lean. There's actually a hit from the undergrad list, which actually I will show you that later, which contains some. There's basically a section on, you know, things that exist in Euclidean geometry. So now we have but basically this tells us more keywords to search for. Like, oh, you know, maybe I was looking for affine space, but now I know that add torsor is a thing, and if I search for it, I'll find a bunch of files, and there's probably a file. There's probably a file called addtorsor.link, and I can learn all about what it is and how it relates to normed groups or affine groups, etc. Or you can look for a definition and then also see what's around it. So like here, I find something about images, and then I look around, you know, what else do we know about images? Oh, images are a subset of another image, or, you know, so, and this will hopefully be somewhat close to all of the things that mathlib knows about these, you know, if they're organized well, then they'll all be sort of in the same area. So you can use this to find what is known about a concept that you're thinking about. Like, I heard that there was something about infinite sums called tsum. I need to do a full research of this. So if I go to where tsum is defined, which I think is this one, then I will see the kinds of things that can be stated about it. I think it's, anyway, So yeah, this is a very low-tech method, but it's useful for learning what's available when you don't have a precise question. Like you're not precisely asking like where's this theorem, but more like what does mathlib have to offer. And of course, you can, another way to start it, instead of just like picking a random file and looking around in it, you can also, if you have one definition, you can sort of pull the thread by control clicking on it, and then it takes you to the definition, and now you can like look around, oh, what else has been done? Oh, locally closed, interesting. Interior, interesting. So this gives you a way to navigate. Okay, any questions about that?
Could you push lecture form? This lecture form?
Beginning. Oh, I did push. No, I didn't push. I committed. I will push material is being edited here afterwards. Thank you.
Quick question, is there an operator for function composition?
Yes.
What is it?
It's well, the name of the function is function.comp, and it can be typed, I think, yes, \O gives you the composition arrow. Yeah, function composition.
Is there one in reverse order as well?
Oh, well, so this is like function composition of two functions like that, right?
Yeah.
Do you mean like function application or
No, I mean function composition.
function composition in reverse? Oh yeah, actually there is. In the category theory library, they like it to be the other way around, and they use this symbol for. But this is the general symbol for composition in a category.
Oh.
Okay. All right. Method number 2 is autocomplete. So the basic idea is you want to know, about some definition, and so you start guessing the name. So you say add left, I don't know, add LE, and then because I have a lot of things loaded right now. Okay, so now I see all of the things that start with add LE. Is there anything? Wow, this is slower than it should be. Or add left something or other. And each of these have statements. So this is a way of basically finding your way to a definition if you know a piece of the name. Now, a critical part of using this method is learning the naming convention, and so I'm actually going to talk about that right now. First thing to know is that there is a page. Where is it? Yes. Page for mathlib naming conventions, and this basically tells you how things are named, and so I'll give you the broad strokes of that. So normally the basic form of it is theorems are going to be in a snake case. So you have types, they're written in this uppercase camel case, and namespaces are also like that. So like this and dot, and then the main part of the name, if it's a theorem, it's going to be lowercase snake case, meaning separated by underscores. So like this. It's composed of several pieces, and those pieces are going to represent. Usually they represent definitions, and there are some connectives. Sometimes there are specific words that are used to introduce specific classes of concepts. So like there's one for intro, so introduction, things are going to be called intro something or other. And elimination, things are going to use elim or rec for recursor. And so yeah, so that's how you get these names, like intro or .intro left, which by the way is also or .inl, but intro left also works. There are also like name components for various common properties, so like reflexivity, symmetry, and transitivity. And so whenever you have something that's reflexive, it's going to have refl in the name. And there's also a convention that it'll be spelled Urfel if it takes its argument implicitly. So here we have reflexivity of EQ. There's also reflexivity for equiv. So equiv is a relation on types that says that two types are in bijection. And so because of that, this is also an equivalence relation. It has a reflexivity. So we can guess that the name of that something is bijective with itself is going to be called equiv.raffle. Okay. Right. And then there are also things for like assoc and com. They mean associativity and commutativity, or left cancellativity. So these are sort of basic patterns. These are actually somewhat exceptions to the normal rule, though, which is basically you read the symbols left to right, and then you start in the conclusion, and you see what there is. So, like here, we have n.suck is not equal to 0. So if you're looking for the theorem that says n.suck is not equal to 0, you would start at this conclusion, and you would read it left to right, and you don't read the variables, so you just say successor not equal to 0, right? And so the name of successor is suck, the name of not equal is ne, and the name of 0 is zero. So this is sort of the canonical name for this theorem. Similarly, mul 0, mul 1, sub add equal add sub is because we have sub. So in order we have subtraction, addition, equals, addition, subtraction. So you get sub add equal add sub. And LE, yeah, so this is, what is it? Yeah. LE if and only if LT or EQ, right? So this is, it's a very mechanical naming convention, and one of the advantages is it allows you to tell the difference between like otherwise very mathematically similar statements. Like if we had this, that's how, I already know what this statement would be if it existed, and this tells me sort of how it looks, right? Oh yeah, probably does exist, but not in NAC, yeah. So here we have, so the one that's in the NAT namespace is about NATs. There's actually one in the global namespace which is about any partial order, and there's one with the opposite order around. So the naming here helps you distinguish which one is which. If at some point it becomes just unambiguous what you're talking about, you don't necessarily read the whole thing, so you might just read the left-hand side. In this case we have neg for double negation equals itself, because what else would you say about double negation? Or pred suck. Now, one thing to keep in mind here is that these, in the display here, it sometimes shows them as postfix operators, but these are always named as if they were prefix operators. So that's what pred comes first.
So, sorry, if you take this example with LE, if, and so on, so are they completely independent of each other, or is the NUT version defined in terms of the general version?
Yeah, so in mathlib, it used to be the case that, well, maybe for a couple of them, there will be a few of these kinds of theorems will be proved enough to show that like less than is a total order. So for instance, like LE total is the statement that A is less equal B or B is less equal A, and that might be proved directly on NAT. And then it's constructed that NAT is a total order, and then thereafter you have the whole library of all total order things, and then usually they won't prove too many other things about NAT. That has somewhat changed recently because these theorems are being upstreamed to lean or batteries, which is another sort of upstream library. And they don't have the definition of total order, but they do care about NATs because it's intended for like people who do program verification and other things like that, where they don't want like a full math library, but they do want the ability to reason about next. So they just get reproved in those contexts. So there is a fair number of sort of duplicate lemmas, and so basically this is being proved independently from this, but it could be, you could prove this easily by applying this if you're in a context where this theorem is available.
But there's no recommendation that says that you have to.
Oh yeah, if you have both of them in scope, like you can use either one. Probably you'll use this one because it's shorter. But yeah, they both work. Right, so infix operators like mul are written as infix. So we have neg, mul, neg is like minus a times minus b. If you want to describe hypotheses, you start from the conclusion, and then you say of, and then you write the hypotheses in left to right order. So here we have LT of successor is LE, right? So the reason for this is they're sort of in order of importance. So like the conclusion comes first, or the left-hand side of the conclusion comes first, because that's the first thing that you want to type, and then autocomplete helps with filling out the rest of it. So this is LT of various conclusions. So LT of successor LE, or LT of not GE, so greater or equal. Here's one which has two hypotheses, and notice the ordering here. So we have LT is the conclusion, and then LE is the first hypothesis, and then NE is the second hypothesis. And yeah, this is add LT add of LT of LE. Okay, so that's how that works. And so as I said, the hypotheses are listed in the order they appear, not in reverse order. So if you have A implies B implies C, you're going to read first C, then A, then B. There are a few sort of slightly macro level abbreviations. So instead of saying 0LT, we'll just say pos. So like here, we want to say that a multiplication is positive, so we read mul is pos, and then the rest is obvious. So it just stops at mul pos, but here we have a more complicated version because there's like, well, if you want to prove that a multiplication is negative, because the first thing is positive and the second thing is negative. And I shouldn't say positive, I should say this is non-positive because this one is non-negative and that one is non-positive. Because they're all LE instead of LT. So yeah, so this just gives you how these things fit together. Now the conventions are not perfect. They don't distinguish between associative operators, for instance. So in some cases, you'll just have to add additional words at the end to specify like which of several variants you're talking about. Or like you might add left or right, and sometimes you also add primes and this kind of thing. But usually at that point, like in autocomplete, you're just going to see all of them, and then you just pick the one that applies. So reasonably enough. Mathlib takes this naming convention very seriously. Here is a example from deeper in Mathlib. Can anyone guess what this theorem is? It's a famous theorem.
Of a Pythagoras theorem. Well,
That's right. This is the Pythagorean theorem, also known as dist square equal dist square add dist square equal pi div 2, which is exactly what is written here. So if you look at the dot comma, you will see that it is the Pythagorean theorem. One of the reasons why it has this complicated name is actually because there's like a bunch of versions of this statement, so they're all kind of have a claim to the name Pythagorean theorem, but if you want to know which is which, then
why it's not a square? They have it duplicated the name instead of the square too.
oh yeah, so the suffix SQ is actually, I think, that's basically code for A times A. So it's square, but encoded in that particular way.
Oh.
So that allows you to tell the difference between that versus. I think also mul self is sometimes used for this sort of thing.
But in the theorem itself, you don't use square instead of.
Well, I think maybe one of the other 17 versions had actual squares in there. Because yeah, you can also do POW too, which is the other kind of square. Yeah, for some famous theorems, they actually have aliases. So like there exists a prime between n and 2n, also known as Bertrand's postulate, which can either be written as exist prime LT and LE2 mul, which is just what these things say, or Bertrand, if that's easier to remember, for instance. All right. So that covers it for the naming convention. But yeah, there is more information on the naming convention page, so you can check that out. So another method of search is the exact question mark tactic, sometimes also known as library search because it used to be called that. So the idea is the exact tactic. You can throw it at any goal and it will attempt to prove your goal in basically one step by applying any theorem in the library. So it just searches the whole library trying to find a lemma that is exactly your statement, which makes it effectively a search tool, right? It means if you want to know, like, okay, here's a theorem, I think it should be true, like, on integers a plus b minus b is equal to a. That sounds like someone would have written in the library somewhere. So I can run exact question mark, and then it comes back with this try this, and it suggests to use int.add subcancel. So that's how I can find these theorems. There's another variation on it called apply, which is when there are some sub-goals. So if I try exact on this, it won't succeed because this theorem is not true, right? If I have natural numbers and I subtract b and then add b, I get back the original. This isn't true because subtraction saturates at 0. So if I take, 0 minus 1 plus 1, I get 1 instead of 0, right? But it is true under some assumptions. And maybe I'm not sure exactly, A bigger B, B bigger A, I don't know, something like that. So if I use apply question mark, it will try to find a theorem that almost solves my goal. And in this case, it found nat.subaddCancel, and there's a sub-goal that b is less equal a, because under this assumption, this theorem is true. It also generates a ton of other things, and honestly, apply is, I would say, not that helpful because it is, the thing is, when you leave open sub-goals, there are lots of trivial things that you can do that don't really make progress. Like you could apply of nat injectivity. Maybe you wanted to prove it about integers instead. Or you could apply DVD anti-sim. Maybe you want to prove that one divides the other and vice versa. So lots of things apply if the goal is to prove an equality. And because of that, you can end up with a lot of stuff. But it's an option. Put it in your toolbox. And I want to show, I guess I should have two things here. There's find and there's Google. I'll tell you about find first, but the interface is roughly that you give it a pattern, so you say hash find, and then you can give a pattern, and then it gives you a list of things that match the pattern. It works, it's somewhat slow, and Google is faster, so I'll just tell you about that. So, Lugal is, it also has a web interface, and actually the next couple tools I'm going to show you have a web interface. So you can either search here, so I can do like nat to nat. And in fact, actually, I tried this earlier and I think this won't work. So maybe not a good example. This will work. So if I search for real.sign, then it gives me this list of all the things that mention real.sign. So this is basically a pattern matching over pieces of the name of the theorem or the type of the theorem. And so you can either use it using this #Lugal command, or you can use it via that web interface. You can also ping the Googlebot on Zulip, and it will also
How?
do this. How? There's a bot.
Okay.
You can do that. And if you don't want everyone to see your Google queries, you can ping the bot inside a DM to yourself. Because it's watching your DMs.
So just for the example that the apply wasn't very helpful, is there any way to know if there's something, like, is there any way to auto-suggest something more helpful?
I
in
mean,
this case?
if you find a way to make apply more useful to people, I think that that's a great feature, like improvements. I think that people have been thinking about this, and if you could find ways to improve it, that would be great. It's not like people want it to be bad.
And is there any way, if it's like a decidable theory, for it to infer the theory and tell you this tactic will solve your...
Yeah, maybe I should have mentioned that as well. So there is a tactic called hint that basically tries the kitchen sink and then tries to suggest something. Or not.
No.
Although, I did give it a false goal, so maybe that's the problem. What was it? Aha. So when I gave it that, it suggested omega. So
Wow.
the omega tactic will in fact solve this goal.
It's a little bit different thing, exact.
That's true.
Yeah.
Well, so hint is suggesting tactics.
Oh.
Exact is suggesting theorems. So if I have won't be a more interesting. Like this, I think. Omega can get this, but I think exact probably won't. Because at this point, it's no longer one theorem application. It's going to be like two theorem applications. I think simple will get it. No? Oh, it partially gets it because I need to give it this hypothesis. If I give it the hypothesis, maybe it will. Yeah, because these are simple. Right. Yeah, so you can search by if you have the name of a constant and you want to search for things containing that constant, you can search for stuff in the name of so like here we have, if you look at these results, you'll notice that they all have differ something in them. So these are just theorems that have differ in some capitalization in them. You can also search by sub-expression, so like you can say times, this thing. If I'm trying to find some kind of pattern of, this looks good. So here, notice that like this times the power occur in all of these theorems. You can search for like, here I want a commutativity result. I'm not sure whether this will work, but I think it timed out. Oh no, wow. Oh yeah, no, it timed out. These methods don't always work, so you can, that's one of the reasons why you want to have a bunch of options available, is because, if you try grep and then you get lost in the library, and then you try autocomplete, you can't figure out the name of the lemma, and then you try Google and it times out, and then you try other things. So, if you have a bunch of options, it increases the chance that you'll find what you want. There are two websites I want to mention. These are basically natural language LLM based let's search mathlib kind of thing. So if I try to search for Hausdorff dimension, then I think it gives me some reasonably good results. This one is something involving dim-h, which is Hausdorff dimension, and I don't know. How about someone else suggest something?
I tried alpha beta search, but it
Ooh,
was horrible.
I have no idea. It found the beta.
Yeah.
I suspect that the issue might partially because mathlib doesn't have anything on alpha beta search as far as I'm aware. But yeah, okay. So that's Moogle, and it also has a inside the editor version, so you can just type #Moogle, and the dot here is required is to prevent you from doing too many queries all at once. It will say the idea is that you type, and then as soon as you type the dot, then it sends the query. Because otherwise, every time you type keystroke, it sends another query, which is a bit rude to Moogle. There's another tool called Lean Search, which I don't know that much about, but I think its specification is not too much different from Moogle. What happens if I just search for algorithms? Best for search algorithm implementation. Oh, I think the difference is that this one is actually trying to summarize what it found. So I think these are AI generated, and the search results are also AI generated. So that's quite nice. And so you can go find something and then go there. All right, and then the last method I want to mention is you can ask people, because people are also good at finding things. So especially if you have like a larger scale kind of question, like who's working on X or Y, like if you're trying to find things that aren't even in mathlib, but like, oh, they're partially on a PR pathway to get into mathlib, then it's good to ask people, like perhaps if you're thinking about your project ideas and like you want to contribute them to mathlib, then you might find out what's the status, not just of things in mathlib, but things that are like on their way, or like someone who's been thinking about it for a while and has a bunch of ideas on how to make it go forward, things like that. So that's there's a Zulip string called "Is there code for X?"
Try reload.
No, it'll come. It's just very slow. Yeah. And you find people like Kevin answering questions of like, oh yes, what is this? This is a very strange. I think Kevin's having a conversation with himself. This is not a good oh yeah, this is a reasonable example. So someone's wondering about how to use some information about sum. So like when you have a sum over some set and you want to like rewrite inside this function f, but you want to know that it's inside the set because otherwise it doesn't matter what is going on here. But if you just use conger, then you won't get that assumption because they're actually sort of separate. And so Ruben has pointed to finset.someconger. And actually, I have just realized that I missed something on my list of search avenues. One of them, very important, is the API documentation, which is this. So you can search in here for, so this is like, if you do these docs links, like what I just clicked on in Zulip, then they will link here. And this is the sort of docgen output. It shows all the theorems. And you can, I don't think, yeah, so you can type in theorem names, like if you wanted to learn about the Hausdorff dimension, then you could go to it here. This might actually be easier than the grep the sources version, which I described earlier. Like rather than looking directly at the sources, you can also just look at this version, which focuses on the theorem statements, which when you're using mathlib, this is probably more about what you care about. But if you want to know how it was proved, you can also click on these source links and get taken to, I guess, this one here. Right. Okay. All right. I think I should take a break now. We should take a break, and we'll come back at the top of the hour.
In link I put already that when we want to evaluate some expression, and this case is a actual pattern match. The first case is 0, but I don't know if they will do a pattern match instead of case 0. Because there is a variable here.
So eval will only evaluate close terms.
Okay.
You can use reduce, and then it will
Reduce.
reduce bars
Okay,
and
yeah.
then it'll get some.
So, two things. I mean, first of all, I mean, I think we have some resources and stuff for like problems domesticated in the Zoom, right?
Yeah.
Have any of those been like required so far, or highly suggested, or like?
I haven't yet talked about project ideas.
Yeah.
I will give you some resources later for that.
Okay. Just wanted to make sure I wasn't like falling behind on that end.
Yeah. I mean, like if you have specific ideas, like great, and you can search, look around for inspiration and so on. But I'll try to also give a list of project ideas.
Okay, cool. I was just curious, like, has there been any sort of work where like you do kind of like hybrid systems, for example, like model checking plus lean or something? I feel like that would be cool, like kind of get some of the
alla sakerna
benefits
som
of lean
har
mixed in
i
with model
idén
checking.
bara indexeras in igen med
Like
samtidigt som
at the high level, that
de
sounds
forsar en
interesting. I don't know. No. I mean, I don't know how it would be cashed out specifically, but like basically that's not yet a project idea. That's like an area idea.
Yeah.
But like sure. Like as an area, that area probably has projects that you could do.
Yeah, I was probably just gonna pick like something from your list of like ideas and things deeply embedded in the Lean community and kind of fun stuff to work on.
Yeah, I don't know how many people are going to be interested in like writing meta programming stuff. If a lot of people want to write tactics,
Kan se väl Schweiz och
for like how you
Irland
write tactics.
neutrala folk ibland.
I think it's kind of fun to just like using tactics, at least for me right now.
Well, yeah, no, I mean,
Tråkig gameplay.
like
Alltså
writing your own
gameplay-mässigt så har ju den här kameran
is going to be
funkat.
Ja,
like
precis.
it requires you to learn the specific
Vi snackar
APIs on
rent
how
varför
Lean does.
politik
Mm.
inte fungerar.
But it's definitely doable. There's plenty, like all the, like Moogle and whatever, like that was not built into Lean, right? Someone created a
Nej,
Vi hör vi
Nej.
neutrala.
Det är sant.
Som vi får snacka
Have you
det här är
done lectures on creating your own tactics?
Men bara ta det.
What's that?
Have you planned any lectures on
Vi var med
making your own tactics?
Men vi var också väldigt
I will if people, if enough
Jo,
people
det är sant.
think that that's a good idea.
Tyskland.
Ja,
Maybe I will have a show of hands about that. And
precis.
then I'll
Jo, det är väldigt
make a
sant. Det är
decision.
väldigt sant. Det är ju...
Men Irland i alla fall.
We can, I mean, if one
Men det är
person or
antagligen
something wants to do
spel-
that, then we can also handle it.
Garanterat.
För då, det är lite såhär, vad är poängen?
Den har ingen riktigt poäng. Den enda som är positivt snabbt är England och så
Trying to figure out
Och
how
ifall
to
den är en medveten
describe
center så skulle det här vara så bra för England.
proposition
Den är
which
så bra för att de måste röra sig på ett fullt sätt men ingen annan kan röra sig dit
Nej.
på ett bra sätt
the sum of all elements of a
tekniskt
set.
sett Frankrike som kan röra sig så men
So the sum of
Of all members of a set.
is it a finite set?
Yes.
So sums over finite sets use fin set.sum.
Right, but I want to describe the set in terms of like it's the set of all members that or of all things that for which a statement is true. So I need to relate like the set description to the fin set, which is described as an explicit list, if I'm correct.
Well, no. So a fin set can, I mean, as long as it's a finite set, you can write down, like an easy way to write down. So fin sets are structurally always finite.
Yeah.
They have to be, but you can, for instance, write a fin set which is you take all the numbers less equal n and then select the subset of them that satisfies some property,
Right.
like filter clothes, right?
Hmm.
And so that gives you a set which is, you know, the property, whatever property you want. There is also a way of just taking an arbitrary set and then turning it into a fin set, and this will turn it into the empty set if it's not a finite set. So then you can literally just write the set of all things such that the property holds dot to fin set, and now you have a fin set.
Oh, will it automatically convert?
Well, it's just a function. It takes a set and returns a fin set.
Right,
And-
but it will automatically decide if it's finite or not.
Reduction?
Yeah,
No, it's
well, like there's an if statement in the definition.
one of the
Right.
classic
It's not computable.
search algorithms.
Oh right, it's not computable. Okay, that's it. Wasn't aware that you can have non-computable functions in Lean.
Oh yes.
So some
Maybe I should talk
game
more about that. Yeah. Like most of this stuff is like most of mathlib is it's just doing abstract mathematics. Like
research
you
onto
have
a
sets, you have
certain
finite sets. You can turn one into the other. But
and
it doesn't matter.
kind of the value of
Only if you're
position
doing sort of
is
programming
kind of symmetric.
programming
so
kind
it's
of activities.
for
Do you really have to
black
care
X
about
minus the
whether
value
things
for
are computable or
for the
not?
one that white is in the position.
But like for the most part, you should
You-
think of this
you
as
want
just
to find your best
specification
move.
level stuff. Like it
So you
doesn't have
take the maximum of
executable
all the,
content. They're just theorems.
possible
So-
moves and then put the black.
So yeah, so I want to prove that
Tries to minimize your
the
score and
set
then
of
you maximize your
lists
score.
such that
Upon and minimize
each
your
list
score.
fulfills
Uh-huh.
a
And then
specific
there is like
property,
a certain
like the
pooling
sum
this-
of
this
these
search
will,
by some
will be have a
parameters
specific
that
number.
sort
Mhm.
I already saw
so the-
a move
For that
sequence
I
that
would
gives me
use
this value.
what
So
was
if I
you said
get
you had
below
the
this, I don't
the
have
fin set dot sum was one
Yeah.
part,
Pooling
and
condition.
I can.
Mm-hmm.
But my
You
main.
can prove this correct.
So how would I describe the final? So I could coerce a set into a fin set.
Project here.
You can. The drawback of using that function is that you don't actually know that fin set has the elements in the set.
Yeah.
Unless the set was finite to begin with. So you're going to have some obligation to prove that it's finite at some point.
Yeah. I have a list to a way to construct like the things, and I want to prove that it is equal to the set. So that's kind of or like equivalent to the set. Like this list, I want to prove that it is finite and it is equal to that set.
Oh yeah, okay, so you can take a list and turn it into a fin set.
Right.
So then you can choose whether in that fin set,
Den här
if and only if.
våren och hösten och vi skickade till Prag.
Well,
Det här är min
You have a list.
Yeah.
You can just
Ja, vi har sandbox
fin
också.
set on it.
Så vi kan göra en sandbox och exekvera och så ser vi vad som
And now
händer.
you can say that X is an element of that fin set, if and only if. P of X, the P is whatever part you want.
Men jag går
Right. Yeah.
And
Yeah.
that's
So
sort of
yeah. That should be
classification.
all the. Yeah, that should be all the
But
steps
then
I
you
need.
flip the
I
value because
I was wondering if there was
yeah, that's
more direct
the
way to relate the set type, but it's
then
probably
Yeah, well, so
Maximize
that
it.
you would also have a set fin set function, but the trouble is,
Yeah,
you still need finiteness to come in at some
Yeah.
point.
Yeah.
I mean, the alternative is you never deal with fin sets to begin with, and you just work with sets. You can also sum sets.
Oh, you can sum sets, but that's also not.
But yeah,
But
there,
I can prove
you can do
things
like
about this.
limiting
the
process,
value is
like
outside
at some
of
point, like
certain
either it's a
range,
finite set
that you
or you have to do the same process
half
into
of
infinite
it,
sets.
and then
It's
you
not
also
really
narrow
But
constant.
yeah,
this interval during.
I was thinking of a variation of it where it was an infinite set, but only finitely many of the elements are non-zero.
That's a finitely supported function that exists. Yes, so you can take sums over finitely supported functions. That's a type called fin sum.
But then
Okay.
you need a value function.
Okay. So the second part is somewhat unscripted, and the goal is going to be to try to define the simply typed lambda calculus and prove that it's strongly normalizing. I have no idea whether I can do this in an hour, but we'll see what will happen. But hopefully this will teach you something about what it's like to formalize this kind of stuff in Ling. And maybe something like this might be a project idea. Okay, so what I've given so far is, everyone here knows about what the simply typed lambda calculus is, right? So we have types and we have terms. Here I'm going to have a base type which is just natural numbers. So I have natural numbers and I have functions from natural numbers to natural numbers, or functions from functions on the natural numbers to the natural numbers, and so on. And my term language, we have natural number literals. So just given an actual natural number, we get a term. We have variables, and I guess I need a index on that, and we get a term. Or we have applications. You can take two terms, you can get a term. And a lambda, which takes a type and a term. And here I'm going to use the parameter presentation because I have no better ideas. So if we want to define strongly normalizing, we have to say what reduction is, right? So maybe we will define a relation which says reduction. So we have a term which reduces to another term. And actually, maybe before we get to that, we should get to the definition of typing. So a term has a type. So how do we do typing? So there's a couple cases. We have natural numbers. So a natural number has the type nat. A variable, well, what type does that have? It depends on the context. What context? Let's have a context. So we have a list of types. This is going to be our context. We call it gamma. And it'll tell us the type of all the variables. So if gamma dot get n is alpha, sum alpha. So we have a type, so you get a variable in the context, and this get is returning an element of the list. Oh yeah, actually, I think I can write it like this, yeah. Maybe I'll do that. So if you get an element of the list, and you get some alpha, then the type of a variable is going to be alpha. Application. So we have to say that an application with app x is type beta if the function has type function from alpha to beta and result x has type alpha and lambdas. So here we want to say that a lambda produces a function on alpha, given that its body in an extended context has type. Okay. Okay, so that's typing, and maybe I should actually, I'll introduce a notation for has type. Maybe I can do this. And unfortunately, I have to do this. Okay, so now I hope I should be able to replace this with like that. Ah, dear. I should. So the issue here is that like the precedence is a bit funny, but I think now it's better. Okay, so that's a very quickly done. Definition of typing for lambda calculus. Simply type lambda calculus. So how do we do reduction? So and we are presumably going to want it to be reduction on well-typed terms, but I think we can do it on untyped terms. So if we have an application, we can reduce on the left. So that, and on the right. And then we can do beta reduction. And I know there's a bunch of people in the room who already know lambda calculus and can probably correct me if I write anything wrong. There are probably also some people who have no idea what I'm typing and might want to ask questions at this point. Is everyone okay? All right, so how does reduction of betas work? Well, we have an application of lambda like this. We have some lambda. And then this needs to reduce to substitution. So we'll have like E dot subst of x. But I haven't defined substitution, so I need to define substitution. So substitution takes a term and another term and returns another term. And the idea is that it's going to replace variable 0. And I believe we won't be able to define this recursively as is. We need to have an additional natural number to keep track of the binders that we go under. This is part of how substitution works in Debian. So we have, so here we're defining a function by, well, so this is just going to be, we have expression like this. And this is just going to be subst n e x and 0. But okay, how does this work? So we're gonna, this is this is the term that we're substituting, and this is the term we're substituting into, and this is sort of how many bound variables we've walked under. So we'll see how this works. So here we're gonna have cases, and then here we're just gonna have variables. And yeah, let me just write all the cases. Okay. So substituting into a lambda, this is sort of where the k changes. I'm going to do this one first. It's lambda, same type, and we substitute a. But we do so under one additional binder. N. These should be in the chain space. Okay. Substituting into a application is just structural. Substituting a natural number is easy. And then the interesting case is variables. And here what do we need need to do. So if the variable were, okay, so there's, I will draw a picture. So we have a bunch of variables like we have A, B, C, and then we have some expression E, and let's say that we're trying to substitute B. So that means that like we originally thought we were going to substitute like we were, if we had something like this. If we have some lambda and we're trying to substitute in the first like free variable in it, and then we go under the lambda, and we're now sort of under one additional layer. What we want to get into is something like this, where we've replaced this variable x1 with this x here. So in order to do that, we have to check which variable it is. So like if the variable is the C here, then we don't replace it. If the variable is A, then we decrease its number by 1. And if the variable is exactly this value here, then we replace it. So if, if n is less than k, then var n. If n is equal to k, then we do something interesting. And if it's greater, then it's var n minus 1. Okay? And what's the interesting thing? That's the substituted value. But it's not exactly just x, because it should be x, but the difficulty is that x, when we call this function, x is actually in this context where it just has the a values, and it doesn't have these extra things that we went under a bunch of binders while we were doing the substitution. So we actually want to lift x by k. So what's left? That's another function that we have to define. So lifting is an operation which takes a term and a natural number, and then it just raises all the variables by that much. And it raises all of the variables, that's a lie. It takes two natural numbers because it has to go under binders too. So we're going to raise by m, and it has a similar structure where, like, if you're underneath these binders, more pictures. So lifting corresponds to an action known as weakening. So the idea is that we will have x in a context A, and then we want to have it also in a larger context, like this AC, which is what we wanted over here. So this is like a lift of x. And then the size of the lift is how many variables we've gone under. But the trouble is that x could itself contain lambdas. So we're going to, so if the number is less than k, so like if the variable that we're substituting is less than the number of binders, then again we ignore it because it's one of these local binders. If it is more than that, then we add this lift amount, n. So that this way, the variable, like, if you have a variable that's referring to something here, then it gets lifted so that it's referring past these c's. But if it was already referring to this because it was a local binder, then it stays the same. So that's what that looks like. And then the others, I think, are structural. Okay. So that's the definition of lifting and substitution for defined variables, which I almost certainly made a mistake because I wrote it live on the spot. And this is tricky stuff to get right on the first try. But you never know, you could get lucky. The default lifting is lifting by 1. Lifting. No. The default lifting is lifting by 1, where your unders your binders. Okay. So I only defined these because I wanted to be able to write this reduction thing. But now at least, hopefully we can get close to stating the theorem that I originally stated. So what does it mean to be, okay, one thing that we might want is, well, what we want is strong normalization, like I said at the beginning. So how do we say that? I wonder whether I can use
What does it mean?
Huh?
What
Yeah.
is strong normalization?
What is strong normalization? Excellent question. How do I write strong normalization? I have a definition of a one-step reduction now. How do I say, okay, we need one more thing, which is a sort of terminated term, right? What does it count as a reduced term? So what's a normal form? This will be a not a normal field extension. Let's put everything here in an namespace. Okay. So I guess natural numbers are a normal form. That's kind of the easy case. And variables are also a normal form because they can't be reduced in the empty context. Wait, no, they can't exist in the empty context. You probably don't want them to be normal forms. Question. Let's say they're not normal. I think we want lambdas to also be a normal form.
So weakhead normal form?
Good question. Do we want weakhead normal form or do we want like fully normal form? I think we need to have a definition of like like it has no beta redexes anywhere in it. Here I think let's do weakhead normal for now because it's easier and because I'm making things up on the spot. Okay, so if something goes wrong, we'll find out during the proof, and that's usually the way things go anyway. So that's fine. All right, so we'll say that that's normal, and now we want to prove that, or no, we want to state what it means for something to be strongly normalizing. And I think this one might just be a definition. So if we have a reduction, no, I know what it is. So a term is going to be strongly normalizing if every term so if every term that it reduces to is strongly normalizing. So this is sort of well founded by the relation of being reduced. I think that's not enough though, because this will still include things that are they have no reduction because they're not well typed, but maybe that's fine, and that's a separate proof.
We have not used the normal form now.
We haven't used normal form. Yeah, instead we've just used it can't be reduced. Which I guess is fine. Yeah, we'll see where it goes. I think that there is another definition that we want to make. Which is sort of so we haven't yet used the typing. Is that a question or is that just
No.
okay? So we want to define some like logical relation, which says that these are strongly normalizing in all the possible ways that you can run them. And so that involves like having terms, because we have this well-typed thing, which we haven't really used, this has type, we want to define like what does it mean to be strongly normalizing at a type. And I think that for base types, that just means that it's strongly normalizing in the usual sense. But for function types, this means that when you apply it, it's strongly normalized. If you have, what is it? I think that's well typed. So the idea is that we have, if you have a strongly normalizing argument, then applying it to this thing gives you a strongly normalizing result. So this is our logical relation. And now I want to prove that this is the part where I cheat and check the math book because I have been making things up as I go along. I can't remember the actual proof. Luckily, I've done this previously and have access to a paper proof. Now, one thing I want to mention is that this is generally what you're going to need to do for you almost always want to have a on-paper mathematics description of what you want to do because it's easier to plan out the high-level details of how the proof proceeds on paper, either because it's been done before and it exists in some book, or you're writing it yourself just to get like the ideas. But you can definitely get into this situation where you write down some stuff and then you're just not clear on where to go, right? Like here's like, okay, here's stuff I half remember from classes earlier, whatever, and then here, you know, well, what was the proof anyway, right? Like someone figured this out, maybe, or maybe you just want to figure it out on your own and try various things, get stuck, etc. But okay, so I'll just tell you that most of what I've written is a simplified version of the simply here the simply typed language calculus also includes products, and I'm skipping that. But this, by the way, is Mathematical Logic by Jeremy Avogadro. I'll send a link later. Okay, but this is the definition of the simply typed language calculus, and this book also has a definition of one-step reduction, and I see already that I've missed a step. We need a rule for reduction under a beta, or no, under a lambda.
But if we have a reduction under a lambda, then we shouldn't. Then lambda shouldn't be normal format, right?
That's right. Yeah. I suspect that once I fix this definition of normal by checking the book, it will tell me to do the neutral terms, essentially. So let's find out how that gets defined. So, all right. So it says beta reduction. Okay. So it's actually going to define beta reduction as a transitive closure of one-step beta reduction, which is what we actually defined, and then beta equivalence. Here's some theorems, which we'll skip unless we need them. But I believe this has... Yes. Strongly normalizing. So here we're going to define strongly computable. That's a better name than Sn prime. SC for strongly computable. So a term of a basic type is strongly computable if and only if it is strongly normalizing. And if it's a function type, then it's strongly computable if and only for every strongly computable term, T of S is strongly computable. So that's what I defined here. Okay, so T is neutral if it is not of the form lambda or pair. Okay, let's define that. So variables are neutral, natural numbers are neutral, and applications are neutral, I guess. Huh? That seems weird. That's what it says. Simple. It's a technical definition needed to make the induction. Okay. Okay, so here's the main lemma. So we have three theorems that one proves. The first one is if it's strongly computable, then it's strongly normalizing. Okay. And I can give this a better name. The second one says that if it's strongly computable and you have a one-step reduction, T goes to T prime. Oh, no, I already forgot what it's called. Reduct. Then T prime is also strongly computable. And then if T is neutral and T prime is strongly computable, ooh, okay, write that down. So neutral. And T prime is strongly computable for every T such that T steps to T prime. Okay. We can actually, let's just say that we know those and then get to the final part. That's probably also going to be needed. Where do we get our final results? I think they. Oh yeah. Oh no, I forgot. Okay. Well, in any case, let's see whether we can prove this.
Would you just like go at a big picture? So
Yeah.
the logical relation of normalizing, strongly normalizing. Like, can you just kind of walk through computable versus normalizing and their relationship?
Yeah. So big picture. What is so strong normalization says so we've got terms of lambda calculus. They can reduce. They can reduce in lots of different ways. It's a non-deterministic situation. But all possible ways for them to reduce eventually stops. There's no infinite path of reductions. That's what strong normalization says. That gets encoded in this inductive type. So the inductive type says that something is strongly normalizing only when everything that it reduces to is also strongly normalizing. And because this is an inductive, it's the weakest thing. And so therefore, if you had an infinite sequence of things, then none of them in that sequence would be considered strongly normalizing. So that's how this definition works. And this is sort of what we want to prove. Strongly computable is actually an additional notion that is introduced just for the purpose of the proof. What we're actually going to show is that actually both of these definitions are trivial. That is to say, something is strongly normalizing if and only if it's strongly computable, and also everything is strongly computable. So therefore, both strongly computable and strongly normalizing are just true for every term. And therefore, STLC is strongly normalizing. That's the idea of like how we make use of this. But in the meantime, we have to define a bunch of things that are saying like, well, if this is strongly normalizing, then that is also strongly normalizing, and so on, in order to get something that we can do induction on. And so these are just sort of a bunch of technical definitions that hopefully will get us through to a proof that every term satisfies this particular property here, that like all of its reduction steps eventually terminate. Okay, so here we have a definition SC, and we want to prove that it's to SN. So I think, well, let's do the induction. This is going to be induction on alpha because SC is defined by recursion on alpha. The first case is easy because that's literally by definition. The next case, okay, so here we have, we're looking at a function time, and if we just follow our nose and unfold this, then we get this, and we can apply, oh no, we have to generalize t. We need this to be true at every t. You'll notice that here t is holding fixed, that's no. Generalizing t, by the way, well, you'll see it in this induction hypothesis, it basically puts this for all t in term here. So now, what is it? So we can apply, so we want to prove that t is strongly normalizing, and I think that's not immediate. So let's double check what happens. Where's our lemma? Here it is. So if t is strongly computable, then t is strongly normalized. So here, in order to prove that something is strongly normalizing, we need to prove that everything that it reduces to is also strongly normalizing. So we can do one-step reductions. I think we need these things to be well typed, though. Yeah. Because otherwise, I think this isn't true. So far, we have yet to use this has type relation at all that I defined at the top here. But that's going to be interesting. So interesting that we run out of time. Well, in any case, at least we've got the definitions out here. And does anyone have any other questions about like STLC and this sort of stuff, or higher level questions about the other stuff we talk about? That's probably a better use of time at this point.
But so, yeah, once like you do all of this, then you don't actually have an interpreter yet. You've just proved that it will terminate, but you don't actually have a way of algorithmically finding the terminal.
Yeah. So this is a mathematical proof. This is just showing some abstract property of some rewriting system. We never really wrote down an evaluator, but that is something that one could do on top of this, right? You could write a function eval that operates on. And actually writing eval was quite a bit easier, especially in Lean, than actually proving strong normalization, because you can just define it recursively. So you could have an evaluator that just returns the object. But here we want to show that like even including these non-deterministic, non-traditional evaluations that they don't loop or something like that. But yeah, this is sort of just a separate thing writing an interpreter.
Mm-hmm.
But I think that's a good time to stop. So, all right, and we'll be back on Thursday, and we'll be doing more formalization, possibly in a different context than STLC. But hopefully, I just want to get you sort of feeling that this is not as intimidating, and that you can feel prepared for your projects that are coming soon. So, all right.
So projects is start next week.
So I'll give you a list of project ideas, and we'll start talking more about like what you guys can do for your projects.